I'm Sarah, and today we're going to be doing some problems with the 4 individual gas laws. We're going to start with Boyles Law. Boyles Law states that pressure times volume equals a constant at constant temperature, and that means that if you keep 2 containers of gas at the same temperature, the pressure times volume in one will equal the pressure times volume in the other. So let's apply that. You have 2 tanks of gas in your lab, but only one has a pressure gauge. It's a 20-liter tank, and it reads 1.08 atmospheres. The second tank is 55 liters, but we don't know its pressure, so let's figure out what that is. Since these are both in your lab, we can assume that they're at the same temperature. Let's set up the problem. P1 is going to be 1.08 atmospheres, and V1 is 20 liters. And we need to solve for P2 when our volume 2 is 55 liters. So to solve for P2, we're going to divide both sides by 55 liters. And we can see now, if we rewrite this out, we have 1.08 atmospheres times 20 liters divided by 55 liters equals pressure. We can cancel out liters because they're on top and bottom, and we're left with atmospheres, which is what we want to have for our final pressure unit. If you solve that, you'll get 0.39 atmospheres. That will be the pressure in your second tank. Next, we're going to solve Charles' Law. Charles' Law states that volume over temperature equals a constant at constant pressure. So again, volume over temperature in one container of gas will be equal to volume over temperature in another container as long as they're at the same pressure. So suppose you filled a balloon to 1.2 liters at room temperature, which is we're going to say is about 23 degrees Celsius. You freeze the balloon to 0 degrees Celsius, and let's figure out what its final volume will be. The first step, since we're working in temperature, is to convert our temperatures to Kelvin. At first glance, you might think that since we cancel out temperature, we don't need to worry about that, but we have 0 degrees Celsius right here, and if we put that into our equation, we'll just end up with 0. So that's not going to work. We're going to have to convert to Kelvin. So the way to do that is to add 273.15 to each of our Celsius values, and for 0, that just gives us 273.15 again. And then we can set up the problem. So V1, volume 1, is 1.2 liters. We divide that by temperature 1, which is 296.15 Kelvin. Set that equal to volume 2, which is what we want to find, divided by 273.15 Kelvin. And to get volume 2 by itself, we multiply both sides by the second temperature, 273.15 Kelvin, which allows us to cancel out Kelvin, and we end up with liters. Cancel these out, we end up with solving for our second volume. The second volume, if you do this math, will be 1.1 liters. So your balloon will shrink, but not by much. Next, we're going to use Avogadro's law. I wrote Avogadro's number, but that's something else. So Avogadro's law states that V1 over N1 is a constant, and that means that it will equal V2 over N2, as long as both containers are at constant pressure. N is moles, as you should know from the ideal gas law or from anywhere else you've used it. So let's solve this problem. You have 2 tanks of gas at the same pressure. One is a 2-liter tank containing 3 moles of helium, and the other is a 1.3-liter tank containing 2 moles of helium. What size of tank do you need to contain all 5 moles at the same pressure? So in this problem, we actually have more information than we need. All we need is an initial volume and an initial number of moles, and we're going to need either a final volume or a final number of moles to solve. We're solving for V2. That means we need to pick one of our current tanks to serve as V1 over N1. And I'm going to pick the 2-liter tank. So we have a 2.0 liter tank, and it contains 3.0 moles of helium. Now, we can just ignore the other tank for the moment because it is at the same pressure, which means that if we used it, we would get the exact same answer. We're going to set this equal to our unknown final volume, V2, over our known final moles, 5.0, which is just combining our 3 moles here and our 2 moles here. So to solve that, we multiply both sides by 5.0 moles. And we can cancel out moles. Oh, I'm sorry, I wrote helium here and I should have written moles. We can cancel out moles and we get liters for V2, which we will find is 3.333, that's a repeating decimal, which we're going to condense down to 3.3 liters. That's how big of a tank you're going to need to contain all 5 moles of helium at the same initial pressure. Our final law is the Gay-Lussac law, And that states that pressure over temperature is a constant at constant volume. Pressure over temperature is a constant at constant volume, which means that for two tanks of the same volume, pressure over temperature will be equal to pressure over temperature. So we're going to solve a problem that's kind of explosive. If you throw a sealed 2-gallon tank onto a wood fire, how high will the pressure in the tank be, assuming it doesn't explode first? The tank was originally at 25 degrees Celsius and 1 atmosphere, and the wood fire reaches 593 degrees Celsius. Again, since we're working with temperature, we've first got to convert those to Kelvin, and after that we will set up the problem. So we have 593 plus 273.15, that gives us 866.15 Kelvin. So that's pretty hot. Now we can set up the problem. P1 is 1 atmosphere, and T1 is 298.15 Kelvin. We set that equal to P2, which we want to solve for, and 866.15 Kelvin. Multiply both sides by our second temperature so that we can solve for P2. And we can cancel out Kelvin, so we get atmospheres, which is the unit of pressure that we want in the end. What we will find is 2.9 atmospheres. So this tank that you threw in the wood fire gets almost up to 3 atmospheres of pressure, assuming it doesn't explode first. And if it hasn't exploded by then, it definitely will when it hits 3 atmospheres.